Okay, thanks a lot. Thank you, Jan. And thanks for the invitation. It's a great pleasure to be here in front of many friends and old friends and new friends. Of course, with some I've been collaborating for quite some time, but it's actually my first time at the university here, so it's a great pleasure. So what I would like to talk about here is on CPS. It's basically two different things. I actually struggled a little bit when I was preparing this talk what I should, because I want to say something about the fundamentals, something about applications. And Jan asked me to talk about both the applications we are doing in energy and transportation. So, which means that I might include a bit too many slides, but I will try to make it. So I will actually talk something about the challenges in both these areas and try to be a bit specific on contributions we have made. And then towards the end I will talk about some more control theoretic challenges, something which comes up in these areas which has to do with how we obtain plant models, how we design distributed controls. So basically three different things, and there are three different teams who have been working with doing this, and you see the names here in these 3 rows. It's postdocs and PhD students and some colleagues. So cyber physical system, CPS, I have no other view than if you go to NSF's website or something like that. I mean, we have these large engineered systems that we would like to monitor and control better, because we are wasting resources in many different domains today. And in there we come together, embedded software, communications, and control in many other domains. I see this when I talk about this in a more popular setting, that it's a very natural development that we have, right? Coming from the networking over the sensor web towards what some people call the action web or CPS now, where some of the distinction feature, I think, that in the systems we are looking into now are the infrastructures. We are not talking about small systems, we are talking about geographically big system. Closing the loop, of course, but also the human. The humans are very important in these systems. As I said, I structure it into these 3 parts. I will talk quite a bit on 2, I call it here, case studies. One problem in goods transportation and one problem in building management. And then towards the last third will be on some cross-cutting challenges. But let's jump directly into this good transportation. So the transportation network is a fantastic source of inspiration if you want to work on CPS, right? Because it is. No one can say anything else, that it fulfills all these aspects of CPS. What is also excellent for a research is that I would say that it's mainly without global control and optimization today. I mean, we run these systems more or less without any type of social optimum or anything like that. And in addition to this, we have all these new technologies around that can make has dramatic potential. But let's look at not transportation networks in general, but let's zoom in to goods transportation, and let's look at the demands from goods transportation. So goods transportation on the roads actually are very important for the society, not only because they secure delivery and so on, but also for pollution, for instance. As you see here are some figures about how the development that we have in goods transportation. 30% of CO2 emissions, for instance, come from this area. And there is a lot of efforts in the world in trying to make this type of transportation more green. Another viewpoint is efficiency. So the figure you see down there from Dr. Ludanek is a CTO of Scania, a truck manufacturer. So when he told me these figures, I was quite surprised. I mean, so 24% of long haulage trucks run empty. These are our Scania figures now, so it's not, but I guess that they are quite representative. 57% is the average load capacity. So you can say that, I mean, there is a lot of waste of trucks going around, where we could use some better method to improve. Another view of this problem is to look from the fleet owner viewpoint. So the one who are delivering, who owns the trucks and delivering, what do they spend money on? And you see that this is basically three things. And the orange thing there is fuel. 1/3 is fuel. The blue, light blue there is salary. 1/3 is salary, and then the rest is 1/3. This is now European figures, but I guess in US it would probably be a bit similar. So notice that this is quite different than if you compare with cars, right? Fuel is not at all that important for cars. For trucks that run 24/7, this is the fact.
Fuel will be a smaller percentage in the US.
I see.
More expensive in Europe.
Yeah, that's right. That's the price is different. Okay, so that was from the demand side. Let's look at the technology push. So this is familiar to all of us, right? We have the sensor and communication technology now, which is there. So today a modern truck have radar, it has cameras on board, it has vehicle-to-vehicle communication, and vehicle-to-infrastructure. All these things are more or less in place, but to what degree they are actually being integrated and used and optimized, that's the second point, but the technology is there. Another technology is real-time traffic information, right? This is also to various degree available. We know what is happening on the road network. We don't use it today to optimize the road transportation, but we know what's going on, right? The third component here, which I would like to spend quite some time in talking about, is vehicle platooning. So this is something which also, I mean, if you look at the control area, the first papers was written in the 60s about this. It's only recently now the truck manufacturers really have taken this to implementation, and we are one of those who are working with, you see this as the Scania trucks, but basically all major truck manufacturers in the world today are working on this. So let's stay with the platooning for a little while. Why would we like to platoon? So on this slide you see on the x-axis the relative distance between vehicles on the platoon, and the y-axis you see the air drag reduction. And if you look at the second truck, for instance, you see that if the second truck is a distance of about 10 meters from the first truck, it has an air drag reduction of about 40%. So it's quite substantial. Unfortunately, 40% air drag reduction doesn't mean 40% fuel reduction, but it could mean something like 5-10% fuel reduction. So it means enough that it's interesting to investigate. 5-10% is a lot. There's two other things you can notice in this plot. One is that even if you are like 60-70 meters or so away, you still have some reduction. And we have been running tests actually up to 100 meters, they can measure some reduction there. The second thing is 10 meters behind, we cannot, the truck driver could not do that with manual driving, right? There needs to be some sort of automatic control implemented. Notice, by the way, that also the first truck, if the second is close by, benefit from this. So it's not an extra drag or something like that. So these three components I mentioned there are there now. So what could we use them for? So let's take a high-level look at this. So we have Germany mapped here. And so let's think about how could we optimize goods transportation. Goods transportation is moving goods now between these cities, right? And what is the situation, roughly speaking? In Europe we have 2 million long haulage trucks, in Germany 400,000. And so it's basically a large distributed control system. We could think about that as more or less like a network flow problem, or an optimization problem, which is maybe not so interesting if we just solve it, so to say, from scratch, because we could not start from scratch here. Because what is the situation? The situation is that we have these 2 million trucks already, right? So we need to come up with techniques which allows us to optimize, but don't do too much harm, right? Don't change completely the way we are running the systems. So this vague goal I put up here, and I will discuss a little bit around that. So how do we maximize the total amount of platooning but still limit the intervention that we make now in the transportation that is going on? So if you were to solve this problem, you maybe come up with something like I would like to show next. So this is like some sort of you can call it a functional architecture for how to solve that problem with these components I talked about. So what do we have on the top level here? The top level is the transport planner, right? There's someone who knows where goods should go between. Well, we know that, and we know where we should deliver. we have a layer here which would be some sort of an optimization layer where we were to choose the optimal route. And as you see in that picture up there, there could be different things. One route could be more hilly, one could be more congested and so on. Decision that you should make where your platoon should be going. And then when you have choosing a road, you have to optimize now, how do I drive over a certain segment here of this road? And here I indicate a hilly road, and I will come back to why hilly roads are more interesting than flat roads in this case. And what you will see from my solution here is also so that, you know, uphill and downhill, these type of segments are the one where you can make some change. These are important, and we're going to come back to these things. But basically, when we have solved these problems from the top down, we come down to the level of individual platoons, and how the individual platoons are formed, how they are split, how they interact with other traffic and so on. Coming down one level further, of course, what we need to be able is to control in real time a single platoon. And the last layer is then how do we control the individual vehicle. And now come an interesting difference here if you, for instance, compare this work with the PATH project in California in the 80s and 90s. So the implementation here is, as I said there, within the advanced cruise controller. So you think about already today the cruise control in a truck is quite advanced. You set a distance to the car in front of you, and you have a radar and so on that regulates your distance or measure the distance, etc. So here you would imagine that you have an interface now where actually the driver swap and shift to some sort of a platooning mood, and then there is some automatic execution going down. And this is, for legal and other reasons, an important aspect of these systems. So let's now look a little bit about what we have been doing, and I will do some snapshots in this architecture of some solutions to the problem, and I will start from the bottom. So if we are to drive a single truck in a fuel optimal way, how should we do that? Yeah, the first thing we can prove from optimal control technique is to say that if we are on a flat road, we should just go in constant speed, right? So we shouldn't do anything. So the interesting thing is when it looks like in the picture here. So we need to know the road ahead of us, the road grade and so on, and then we can adjust the driving according to that. And we formulate some sort of a cost function which is basically fuel cost. So this is nothing but, so to say, what the fuel cost would be for a single vehicle there, which of course, as you see, for instance, depends on the alpha, the road grade, the air drag, etc. And then we have the dynamics, and then dynamics we just have from the Newton's law of physics, right? And you see again that it's very basic. We have the drivetrain, which gives us some force, F engine. We have the braking force, FB. We have the air drag, FAD. We have the rolling resistance, FR, and we have the gravity, FG. So what makes this problem interesting for a truck, but not for a car, is that the truck here could weigh 60 ton or so, which means that when we are going uphill compared to going flat, the forces that act against us goes from being the air drag and the rolling resistance to being the gravity. So we basically have a switch there in this equation, and then we can solve the optimal control for doing that. And this has been done, and this has been implemented. And if you buy a Scania truck today, you can buy this feature. Of course, they don't call it receding horizon control; they call it eco cruise control or something like that. The feature is also for the driver very reasonable, because if it's a light truck and it's not too steep, what you see there is that you just go in the constant speed, right? While if it's a heavy truck, what happens is something which the drivers already today are doing. You speed up a little bit before the hill going up, right? And then when you pass the hill, you then go a little bit slower. So this is a very natural thing. The thing is that you now do it in an automatic way. And remember this, that everything here now is implemented on the velocity reference. So it's kind of implemented in the system as you would expect the cruise controller will be doing here. There is something which is needed here, which is not readily needed today. What is that? So for this system to work, I cannot just implement it and run it like this. There is some piece of information in these equations which are not there. What is that, John? No, there is no communication that is needed, but there is a variable here that is needed.
What about the weight?
The weight? No, the weight, today these trucks estimate their own weight continuously. They don't do it very well, but they have that estimate.
Wind?
Sorry?
Wind? Doesn't matter.
No, wind is not.
Is there a car in front of the truck?
No, but it's what I was talking about. It's alpha. It's a road grade.
The grade,
Yeah, you don't get... Oh, you said the grade, sorry.
No, I didn't say it, but I was thinking you
Yeah.
It's not anything.
No, so the road grade, if you think about your navigator, right, you don't get the road grade out there. There are Navtech and others are out there measuring road grade, probably in US just like in Europe, but now they sell that. And when we worked on this project, we've been working on this, you know, you just ask this question. So why do you have to buy this thing? And could you do that? Could you actually get the road grade? And this is one of the things that we actually have been, it's a little bit like a separate project, you can say. So we develop a distributed road grade estimation, because if you now are a truck company like Scania, and you have all these trucks around, I mean, you have all these mobile sensors. So what you can do is now that you estimate the road grade, right? You basically do what Navtech and Google are doing. You do it yourself. And this is what we've done, and you see up there to the right. I mean, it becomes an extended Kalman filter. Yes, please.
When you say estimate, because if I go from the same road, I know the grade, and I can store it.
Yeah. And this is what you see. I mean, actually, or you maybe don't see it in that figure. It's a bit small here. Yeah, so you have a Kalman filter here. You do some smoothing, some data fusion, and some storage. So you have to go through this different steps. The challenge, the interesting challenge here, I would say, is to keep track of the quality, because how much information would you like to store, and how would you like to share that around the vehicle? And basically the way it's done today is that you make sure that you have had enough vehicle that have traveled, and then you store that in a unit, and then you use that information. But and what you see in the figure there is just some runs with different number of vehicles, and you of course get improved quality as you are traveling around this. So that was a little bit a separate thing, just to remember that we need the road grade. So if we have the road grade now, and we know how to plan this for a single track, we need to also be able to do it for a platoon, right? And again, for the platoon, the difficulty is when we go up a hill. And this is now a little bit more tricky now. And I would say in general, if someone would like to solve this problem, I mean, there, as far as I know, there is no one who told what was the truly optimal solution here. Let me explain why it's difficult, because as you see in these equations, in this case now, the air drag depends on the relative distance to the vehicle ahead, right? And also to some extent also to the vehicle behind. So you could now think about an individual truck in this platoon. Should he follow what is his optimal trajectory for himself, or should he stay close to the others? Or is there some sort of a trade-off? And we have been looking into this problem, and you can see just in general there are different solutions that you see there, different strategies you can say. Should you accelerate a little bit before? Should you allow now the distance between the vehicles to be a little bit smaller for some time and then increase again? Or should you try to make the distance a little bit bigger before the hill, and how you should do that? So that's an interesting problem, and we have come up with some heuristics and have been running some tests and so on. But in general, what is the optimal thing for this is not known. Okay, so let's then continue with another interesting problem here, and that is how to form the platoon. So with this picture, we just want to illustrate how you can think from an individual driver's viewpoint who is already out on the road, right? You could imagine now that for me here, I could think about who should I catch up with, and who I should catch up with would depend on where they are going and what distance they are from where I am, right? Everyone goes more or less the same velocity, but otherwise that would also be a parameter. And you could imagine, of course, that in this situation you maybe benefit more if you take a platoon now which is closer than one which is further away. But okay, so with that, before talking a little bit more on the higher level issue, I just want to show you a couple of very brief movies just to see how a little bit things are doing. And there will be two different things. One will be how the communicator at Scania sees this. So this is more like a professional producer. And then I will show some of our experiments. Does this show okay there, or is it okay? There is no sound, but it's just, as I said, it's just an illustration of this concept. So you have the track out there, and the tracks are forming these platoons. They are forming them as they go, and of course they now communicate back and forth to keep that short distance I talked about. And of course, a question that comes up is, what should this distance be optimal? And we have some idea about that, and we have run wind tunnel. Something which is an important issue here is the safety, right? And other drivers. And this, I would say, is largely an unsolved problem so far. How to be able to do exactly what is happening there. Or imagine that it's not a car, that it's a motorbike, and how should you now detect this? There is another scenario here when a truck now will be leaving the platoon, but imagine also that there is an on-ramp. How should here is kind of something like that, which I think is a quite challenging task to show in reality, that you have this automatic lane change, right, and everyone follows automatically. So this is somehow the view, what this system is supposed to be doing. Let's see, just so since I talk a lot and I show equation, let's show some real stuff. This is a couple of years ago, before we were out on the highways. This is on a test track. This was on the Swedish Evening News. So these are 3 trucks running on this test track, and you see that they have antennas here on top. And basically, the first truck is actually run by one of my PhD students, and the other 2 trucks are then automatically being controlled. This is how the journalists compare this the air drag reduction, right, with the Nordic cross-country skiing. This is what you will also see here is that in the second track here, actually the journalist is in the this is the collaborator. Let's see here. You will see in this track now the journalist is actually behind the wheel, and is reporting about this. And you see he doesn't touch the gas pedal, and as you will see soon, this is also automatic steering. So yeah. And as a researcher, you can imagine, I was very, very nervous at that. I was, we have had in the past some other type of experiments where things can go wrong at this moment, right? But things went fine, so and it's still going on. But let's continue move up on this in this hierarchy now, and so come back to this high-level problem now of optimizing the goods transportation. And we say that we have this technology, this platooning technology in place. So basically, what we can think about is that, okay, this is like a snapshot of Germany now, of the Autobahn system, and there are trucks around. So one thing one could think about here is now, what about if we took this truck and while they are driving, we suggest that some of them should merge and go in platoons. So basically implement something that you see in this picture. So we suggest intersection points where the highways are merging, where they actually go together in order to optimize then the maximum platooning. And in a particular situation here, you could end up with something like that, where some of these red ones are actually platooning and some are not. And of course at each junction here, or intersection, there needs to be some sort of an intelligence, something that predicts now when will track be at this intersection, and who should speed up or slow down just a little bit, because you cannot interfere very much with the cruise controller, right, in order to meet perfectly at these intersections. So let's say that we were doing this. Would this solve the problem? So we have been doing we showed some simulation and some experimental data here. So first the simulation. So let's say that we now take 300 trucks over Germany, and they have random starting point and destination in German cities, and we run 500 experiments. How much would they save in there by the platooning here? And you see there that most of them, or the mean there is something like 2.2% or something like that. We assume that if they platoon, they save 10%. So, but in average, there is a saving of 2.2. So not very much. But this was 500 trucks. So then we increase the number of trucks. So here you have the saving on the y-axis and the number of trucks on the x-axis. And you see that that point, the 300 track point is there, right? So it's very, very small. But we see that if we are over here with 4,000 trucks, we are up to substantial benefit. This is just like now randomly distributed, right? But it still gives some indication. And why we did this study was actually just to argue for that this is an interesting and a possible concept, because it means that for German situation, 2 to 4% deployment would be enough, right? If this technology was in there. Yes, John?
Usually trackers are paid by time of delivery.
No? No, the way...
Let me ask something. Is there any studies of the effects of platooning on the time to deliver, the time to be there?
We are doing that, but it's you know, the deliverer, I was told is basically that they have very hard deadlines. So if you go from Stockholm and you should deliver something in Madrid, they have a 15-minute window when they should deliver. If they are not there in time, it's like you miss a plane, basically. Okay, come back when there is time. So they're very tight when they should be, there. So this estimating the time of arrival is very important. Right. And there is, so one reason or part of the whole thing here, which is integrating more information to be able to make better decisions, is just this as well, that you could actually more precisely estimate if you are going to meet that deadline or not, or if you can maybe do other things in order to try to meet these deadlines.
Because this translates to economic value in addition to the fuel cost.
Yes, yes. Right? Yes.
If you're late, basically this is just the penalty.
Yeah. And one reason how it's done today is that often around cities you have hubs where the long haulage trucks deliver to these hubs, and then you have local deliverable. So it's basically a buffer that they construct just in order to be able to meet these deadlines. So it's like what we sometimes have been doing in communication systems as well, right? You have these buffers in order to deal with this. Okay, but let's look at some real data. So what you see here now is a snapshot of a region about 650 kilometers on the side here. Of somewhere in Europe. I'm not allowed to say where it comes from. In this plot there are 2,200 Scania trucks now. So what we did over the summer basically, and was to track some, to see how do they drive today. And what you see here is the same, but we now use a sample. So the position of a truck here are sampled every 10 minutes, synchronously. So we took this in this particular picture for 14 trucks, and you can spot here, you see that there are some trajectories, right? Here is one truck going on this highway, there is one going on this highway, and so on. And then we asked the following, so are they close enough in time and space so that they could, if we would have this technology already in place, be in platooning? And how could we check that? Yeah, the simplest thing that we thought of there was that, okay, just put some radius around them and check how many others they have around, and so if they would be platooning. And you see this is the result there. It's not too deep, right? But it just says that, out of this 875 long haulage truck that we had in this region, if we look very close, of course there are not many that potentially were together. But if we increase this region a little bit, there were quite a few. In this case, the savings is very small because we are looking at longer haulage over basically going over Europe. So it's not so many that would share the whole distance, but you see that many share some segments, and that's basically what that figure is saying.
Can I ask a question?
Yeah.
Okay, back to time now.
Yeah.
Why does it make sense that when I'm the planner of this, I may delay some tracks or may accelerate or the departure of tracks so that to make this more possible, at the same time, not deviate too much from my delivery time.
Yes.
As for instance, is done in air traffic control.
Yeah.
Or other transportation systems where you try to balance things up because you want to have people on the ground only certain hours and not 24 hours and so on. Is there some coupling there that should be considered?
Yeah, I think very much so. There is no details in this which had borrowed, I would say, from the air traffic management or the logistics and so. But there is definitely intersections on how problems are solved, which I think maybe a difference here that I see is that this business is, even if the truck manufacturing, there are a few big ones, and there also the fleet owned, there are a few really big ones like DHL and Schneider and this or Schenker and so on, right? But there is a lot of those who have maybe 5 trucks, 10 trucks, 50 trucks, and they, are very important in this picture, how to integrate them and how they would benefit from that system. So, and that might be different from in the air traffic, I think. Something on the other testing. So since a bit more than a year now, we are running also tests between Stockholm and Zwolle, city in Netherlands, running this 24/7 with truck drivers. So you see here there is something like 20 trucks and 65 truck drivers, also studying their experience of these systems and so on. I won't dwell into the results and so on, but as you can imagine, some of this goes into the acceptance of the technology and so on of this. This has also been you saw this thing I showed earlier in the news and so on. Okay, so with that I would like to switch to, this was so to say the first case study. I would like to switch to the second while I understand that maybe it will be tough with depending on how many questions John asks now in the next section. So let's talk about building management. So it's still a large scale system again, where we also want to save energy. The same components come in, but of course the domain is quite different. This is Stockholm. If you have been in Stockholm, you maybe have been to one of the royal sites. You see the castle up here, and you see the Royal Institute of Technology. You have the Royal Academy. If you are coming for the Nobel Prize, you don't get it there, but you get it down there. But they have their building close to KTH. But this is not what I put, but this picture. There is a sustainable city district that is being built and people are moving in right now, which is called then the Royal Seaport. And that is over here, where this picture there is a harbor, and this is what it's being turned into. So, and this is, we talked about Clinton's initiative earlier this morning. So this is part of this Clinton Green City initiatives, and there is a lot of constraints on the CO2 emissions and so on this city. So we are involved in some projects related to this, of how to do more energy efficient buildings. And this picture about energy consumption, you are probably all familiar with, that buildings is a substantial part. In Europe, it's 40% of total energy is used in buildings. And also to notice that 76% in building energy is for comfort. So it's a lot for that. So are we doing this the right way? And there have also been some general studies about this, that actually with information and communication technology we can improve this a lot. So there's a lot of potentials here. And when it comes to making buildings more efficient, there is different technologies being developed and different works going on. I want to focus just on one piece that we have been working on here, which has to do with HVAC, optimizing the HVAC system. So HVAC is heating, ventilation, and air conditioning, right? And the classical control problem, and if you want, you can say, yeah, it's nothing but an optimal control problem, right? You want to reduce the energy you are using in keeping the building in a good condition. Keeping in good condition is basically keeping two variables into some constraints, and that is the indoor temperature and the air quality. So this is what we are dealing with here. And we started to work on this a few years back, and when we started, the first thing we realized is that we are inside a building, right? So we started to develop a test bed to understand better what this is. So after quite some work, we get access to the whole SCADA system, or the whole control system of the KTH campus. So we have access to that in our system now, and we are located EE in that building that I ran in, which looks like this. And in one of the floor plan there, we have worked a little bit more actively in also changing the system. And in this floor plan is a basement of the building where we have some labs, we have some lecture room and so on. If we look inside one lab, it looks like this. So you have a room there, and you see it's a student lab doing the basic control courses with the double water tank processes and so on. And as I said, you have some actuators, which are the traditional one. You have some air coming in here that is heated or cooled. You have some hot water coming into the radiators. And you regulate also the fan, the speed with what air is coming in. And you have some sensors, the CO2 and temperature sensors. But we also did here is that we included some more sensing, right? And the type of sensing we have included is like a people counter and so on, weather station. But also thinking about information that you can get from outside, like occupancy schedules and so on. So this is being integrated here. Of all these things, which has been the toughest thing, is the first line. So we actually got a PLC integrated into the real system. And it was not easy to get all the permissions, and I don't think we really have all the permissions, but anyhow, we have a system running there, right? And it's actually available, so if you're bored by my talk now and you have a smartphone, you can go into this homepage and you can actually read online what is happening in this room now. But I would like to say something about the control we are developing here, and the control architecture. So we have been developing a new control architecture for this HVAC system, which on the low level have the existing PI controllers. As I said, we are regulating the air flow, the supplied air temperature, and the temperature to the radiator, right? So these are the control variable. We are measuring basically here the CO2 concentration and room temperature. So what is new here now is this other type of information that we get in, like the weather forecast and things like that. And that comes in, and the way we integrate it here is through scenarios. So the thing we have been developing is scenario-based MPC. So we basically, what we basically have is that we have an architecture here where, first of all, notice that there are two different controllers here. So the temperature controller is the one who are acting on these variables. The CO2 controller is only providing a minimum airflow that is a constraint to the temperature controller. So because the CO2 is more like we view it here. Of course, you can argue if this is the best way to do it, but we view it here like it's kind of some sort of a minimum that you compute. And then into these comes now these the models that we have of the weather and the occupancy. And I want to talk a little bit about how these are being integrated. Some of you have maybe seen this about scenario-based MPC, but if not, I will say a few words about that. But before that, let me just show you something which has been very important. Of course, to do the control, to design this controller or to tune this controller, models of this is very important, right? And models here, when I started this, I was a bit naive. I thought we go to a textbook on HVAC, right? And then we write down the model and that's it. But actually been quite some time in getting models on that level that we can use here. Of course, here it looks very simple, just linear models and so on. But to get, so these models here that we derive are a mix of physics-based and system identification type of models, right? Or gray box models, if you want. After a lot of work, we are on the level that we are quite satisfied with these models, as is illustrated with this. So this is some days during this summer. You see, you have the measured data being the gray line, and the solid one is the predicted, just simulated open loop from this point, right? And you see that it captured, the CO2 is captured fairly well as the temperature is also. It's not perfect, but notice that here it's single degrees. So we are talking about a granularity down to tenths of degrees. So it's pretty good. Okay, so now let's look into these the MPCs there and see how do they work. So the MPC for the CO2 have some constraints, right? One class of constraints are just the regular type of deterministic constraints, like the input here needs to be within certain bounds. But in addition to that, we have so-called chance constraints, or we have probabilistic constraints, which says, for instance, that the air quality should be within certain value with a certain probability. And then we minimize with the MPC a certain cost function, and we implement the control according to the equation here. The same with the temperature MPC. Similar, right? But different equations. In this case, it's a thermal comfort. We should, with a certain probability, be within this range. So how do we now go from the chance constraints to the scenario-based MPC? So one way could have been to stay in the stochastic world and do a stochastic MPC, but we don't do that. We do a robust approach instead. So we translate this chance constraint into deterministic constraints. And how do we do that? So the way we do it is that for one of these disturbances, let's say that it's a weather, we see that the weather into the future have two pieces, one that we can forecast and one which is a forecast error. And with these type of things like weather, occupancy, and so on, assuming that it's Gaussian and so, it's not a good model. So that's why we are using this approach. So we try now to come up with other types of probabilistic description of this, which comes from, could be like a mix of Gaussians or other types of underlying probability model that could be learned during the operation of the buildings. When we have that, we can generate scenarios, and there is also some theory here developed by Karl and others of how many of these scenarios you need to be able to put into your system to compute this robust controller in order to guarantee with a certain probability that you satisfy these probabilistic constraints. So you see that in the end you get some sort of a robust formulation of the MPC in. So how well does this controllers now do? So on the middle plot here you see in the gray line is the existing controller. So the existing controller is able most of the time to keep it within the comfort range, which is 21 to 23 degrees here, but it exceeds at some point. And so the new controller here is doing a little bit better. This is the control action, and you see there are two types of control action that I showed here. One is the supply air temperature, which is this that varies here a little bit, and the other one is the airflow. And you see the airflow is more or less bang bang, right? Either it's on or it's off. It's not per se bang bang. It's not a discrete variable, but this is the case. In our case, you can see that what the MPC is doing, what is a bit different here, is that it's more active on the temperature of the supply air. And this is what does the job. Okay, so how much do we gain by this? And we gain something like 8% better than the existing controller. If you look at the absolute number there, you would say, why caring? This is extremely small, right? But remember, we're talking about one room during 6 hours, a summer day in Stockholm. So I mean, this you should view on a bigger scale. Okay, so that was what I would like to talk about in the building management. And for the last 10 minutes, I want to talk about some of the cross-cutting, or some, I call it cross-cutting here. You will see if you think it's cross-cutting or not. Okay, so let's go back to the cyber-physical here. Some year ago we talked about, okay, what are the challenges in CPS? And of course there are a lot of different challenges that comes to the scale of the system, to the radio, etc., etc. Here I want to focus into something specific. I call it here program that assemble. What I mean by that is the thing that we developed local mechanisms and we still are able to achieve some sort of a global behavior. In the control area that has been considered quite a bit, right? One type of problems, we sometimes draw a block diagram like the following, where we have a lot of different plants and a lot of different local controllers that are now controlling the system, and we ask ourselves, how can we develop control for these type of systems when we now have this type of demands on the global objective, on the dynamics, restrictions on what we can compute, what we can communicate, and so on. And a particular class of problem are the one being dealt with in decentralized control. So in decentralized control, we focus into just saying that we have some plants given here. We know the dynamics of peace. And then we will have method to find out what are good Cs. And since 40, 50 years, people have studied that problem. But one thing that I'm not going to talk about that problem. I'm going to talk about what I think has been studied too little. And that is that if we now think about that block diagram and relate it back to some of the application I talked about, who gives me these P's, right? So the classical theory assumes that we have information about the PIs, right? And I argue that these are not so easy to get in general. It requires quite some effort, and like that Rome example I showed you. So what if we should design, for instance, C1 in that picture only based on information about some of these P's? How should we be doing that? Or if you want to ask that same question on the platooning example. So let's say that we have a free vehicle platoon here and we want to regulate the inter-vehicle distances. Should I now communicate the mass between the vehicles or not? How much benefit is it in communicating that? And that is an interesting question if you think about it, how you implement this in a real system. Because communicating the position and velocity you typically would do, right, to your neighbors, but you maybe don't think about the plant model. And of course, the plant model plays a large role. So how can we deal with that problem? I will try to spend a few minutes formalizing one problem related to this, and then we will conclude. And I will start with an example coming from a paper by Langbot and Dulvin, 2011. Very simple 2x2 system. We would like to minimize an LQ cost. We want to keep that small, but let's say that we have state feedback, so we have x1 and x2 available. How should we do that? How should we do that if we only know A11 and A12 for the first controller, the one controlling U1, and vice versa for U2? And I think, we don't have time to ask you now, but I think you all would come up with that, yeah, you probably just cancel the dynamics, right? You will do something like a deadbeat. So you would assign U1 being negative what the rest of the right-hand side is, and then you get a 0 on the right-hand side. So it's a deadbeat controller. What you can notice if you compare it with the optimal centralized controller is that we achieved something which will be better than twice the optimal centralized, right? So, okay, so what? So what they proved in that paper was, basically the main contribution was to show that there is no other control strategy that could do better if it also had that type of limitation in the plant model information. Okay, so this type of thinking now about, do I know the model or not? And how can we deal with that? That I want to talk a little bit about. If you're not motivated by what I said with that example, let's look at this a little bit from a high level here. So one thing about limited plant model information. One thing there is that it's basically done already today, right? If you look at how a process industry is being controlled, the complexity for the controllers are very important, and you cannot let them depend on a lot of global models, right? It's only local. Of course, it's a lot of heuristics going in there, but it's local. The availability you can think about for the platooning, right? You cannot know at the design phase who you're going to platoon with, what parameters it has, and so on. A more interesting recent thing is this about privacy, right? If you think about the control of the power grid, there could be so that some dynamics you would not like to share with the others because it could be an economical benefit of that. So let's try to put this problem into a networked setting. And with a network setting, I mean a traditional network control system where we have controllers K and plants P, which interact as I draw there with the arrows. I will use graphs now to show the links here. So I have something I call the plant graph, which just shows what subsystems, what sub-Ps here are interacting with which. I have a control graph which illustrates what the controllers can do and what the controllers what the information the controller has. And then I have the new thing, which is what I call the design graph. So when I design each of these controllers, I say that there could be different amount of information available about the plant. So like in this picture here, a self loop here means that when I design this controller, I have only information about P1. While for the others I could have more information. So this is what I mean by having this model information limitations. So let's very quickly just put some linear systems notation of this. So we say now that P is given by a linear system and that we have a structure now which is given by that plant graph for the plant, right? And that puts some structure given by the adjacency matrix of that graph on the A matrix of the overall dynamical system, right? And we have a B matrix that supports this. Similarly, in what I will show first here, we will say that the controller is just a static state feedback controller. Again, the controller then have a structure given by the plant graph, which gives some structures on that matrix K in the control. The design graph now, the design is a map from the parameters of the system, so from A and B to a controller to K. And now the part of A and B you can use when you compute K is restricted with that design graph which I have down there. So for instance, in this particular case, you see here I would have a design graph which looks like this. So why would this be reasonable? If we look back on the HVAC, for instance, you have a floor plan here. You can imagine that the different rooms interact through the temperature or interacting to rooms which are next door, while in the design graph, it could be still so that I design the local controllers only based on the information that I have of the dynamics in that room. How can we compare performance of different design strategies now, or design methods gamma? We use the concept from computer science called the competitive ratio. So I basically say I compute a cost J of this gamma of the design of AB, and then I take supremum, I take the worst case of all the plans I have, so I get something there, and then I normalize that with the best possible thing I can do, the K star, and then I get a quota out there, which I call the R, which is a competitive ratio. And then I do that for, in this case I have linear system, I will do that for a quadratic cost, and I notice that if I have a complete graph, so I used state feedback where I used the full K here, then of course the best thing we can do up there would be the usual optimal LQ controller, right? Okay, so with that notation we have come up to a problem formulation. So the problem I'm interested in here is now to find good control strategy that minimizes this competitive ratio, given that we have structural information about the plant, about the controller, and about the information available. And I would like to understand how do these different graphs play a role here. There is some assumption in the result I'm going to show. The most important is the first one. We are currently, the particular thing I'm showing here is for fully activated system, which is of course a strong limitation, that one can do some extensions here. Notice that the first example I showed you, that we came up with a deadbeat, and that deadbeat also fulfills this condition that I put on the design information. And what is interesting in this network setting is the following result, that basically the result of Langbot and Deleuze extend to this setting of networks if a condition is fulfilled, namely that the control graph needs to be a supergraph of the plant graph. And what does that mean? It means, so with supergraph here, it means that it has more edges than the plant graph. So just in some sense means that there needs to be more communication in the controller than in the plant graph. So if that is fulfilled, it's still so that the deadbeat controller is never worse than twice the optimal controller. Okay, that was for the deadbeat. The interesting thing here is now that holds for any design strategy in this setup. So it doesn't matter what gamma that you, what design strategy that you are looking at, as long as you look at this type of state feedback. So as long as in this case the design graph is fully disconnected, you can never do better than that. And as you see here, I talk about sync here, but it's just that in the other case you have to go a little bit further. But I will skip that. I will skip this example. I will also I think I skip. I have some. Let's come to the conclusion, so we have some time for discussion here also. So what I tried to convey here today is, one thing was about this CPS architecture. I think there are some open questions about how this architecture should look like, and just working with a couple of application domain, you see that there are some similarities on how we, from a control, communication, computing viewpoint, would model this system, but it's not at all there, right? I talked in the end here a little bit about this thing about local plant models and global performance. Something I hinted to but didn't talk much about is testbed development. So implicitly here, something that we have invested, I would say over the 5 years, a lot of resources in, which I didn't do 10 years ago, was actually in working on developing test beds. And you see some of that also down on this picture here, but it's been more and more important to actually be able to show that these things are working in some sort of reality, even if it's in a student lab or so. If you're interested in the work and you are not yet on my schedule, the papers here are on my homepage, and I can put up the slides there as well. So, okay, thanks a lot for the attention.
Thank you for a very interesting talk. Just want to remind everybody that we'll have a round table tomorrow at room 1146, 11-12. Professor Johansson will be here today and tomorrow, and you can talk to Regina if you want to see him. There's still some slot tomorrow. Questions? Okay, so I'll ask the question. Well, go ahead.
Yeah.
I don't know much about this area, but I've seen some papers that talk about something called co-simulation.
Yeah.
Do you do that in your work?
Yeah.
Simulation?
Yeah.
Is that part of it?
Yeah, we do. I mean, code simulation basically is about that you would like to so to say, model from different domains, and you would like to see, so to say, how if you have the implementation of the controller, you want to so to say run a simulation of that controller with the physics in the loop and so on.
That's right, and then update the controller and do optimization like that.
So there is a lot in general in here. There is a lot of that actually. One thing is, if you look at the model, if you go to the truck examples, so the most hi-fi model that we have of the truck is a Modelica model about 1,000 states, which is so detailed, so we are able to get fuel consumption out of that model to some reasonable degree. If you look at the other in the build, if we also tie to the building case, I work with people in the building from the building sciences at KTH who develop things like you would call something like Simulink or Energy Plus or something like that, which can do certain things very, very good. And then certain things is much harder, like, for instance, implementing different type of controls and so on. So we try to work with them and understand how can we come from these different domains and be able to simulate things together. Yeah.
Great, thanks.
Yeah. So in your building case, did you do this experiment across seasons? That kind of efficiency is there across seasons, or that was kind of an average, that 9-10%, or?
No, that was yeah. That's a very good question, because there is another question there. Let me ask myself one question that you didn't ask about this, because if you think about doing this, so doing this thing, right? So now I say, so let me ask myself my question first, and then I come back to yours. So how did you do? So this is during one day, right? And I say between 10 and 2, and then I say I can compare my new strategy with an old strategy. How did you do that, right? Because it's one physical building. So what we did in reality was that we actually took 2 similar days. So similar the amount of sun and the temperature outside and so on. So this is one thing that it's just with doing the comparison between different strategies quite hard, because you have to be careful about that. We are running more long-term tests now, but and that is one reason why we developed this test bed with the server and so on. So we are actually storing a lot of data. And I had a guy who developing this, just the system to store the data in a secure way and so on. I said, you can actually hook up to this system online. You can download a lot of the data if you want, about the occupancy and about the temperature and so on. So we are doing this, but we haven't done like a test over a year and see how this compares and so on. In general, in Sweden, I mean, we are coming into the cold season now, right? So in December, as you all know, right, in January or so, you will have a much bigger benefit than, I mean, June, July would be the so to say, the least energy that would be used. So this would be, so to say, a bad case to show if I would like to advocate the control.
Sure. So is there any pre-cooling done? Like when you're kind of, let's say, in your strategy that you take the occupancy schedules, you take the weather schedules or weather external weather into account.
Yeah.
You also do pre-cooling? Like, and let's say you're trying to...
So locally you mean, or... So if you look at the architecture, so this is what it looks like. So here you can cool or heat. You see there is a plus and a minus, the air.
So actually what I was referring to is that, let's say there's nobody in the building in the night, and you just cool it so much that, based on the next day, the cooling it starts up at a very low initial set point and you don't require...
Yeah. But you have to separate 2 things, right? So there is the general cooling or heating of the building. If you take now, then, so we say heating is so this you typically don't change very much, like the radiator. And then what happens is that when people are in the building, you run the ventilation system. And another interesting side effect, that with our system now we detect, I mean, so basically at KTH they switch on the ventilation system in the morning, 8 o'clock, and then they switch it off when the last guy leave. Not the last guy who is in the building leave, but the guy who operates the building leave, 4 o'clock. And we run labs in the evening. And actually with our system... Oh, you have seen the data? Yeah. So actually so I had a couple of people who worked on that to send me an emergency email a couple of weeks ago, because they detected that the CO2 level, like 9 o'clock in the evening or 10 o'clock in the evening, was more or less on a level in some of these labs which were, it's not good for your health. And it's this type of things that you can detect when you start storing the data. You can, so I mean, there goes in a lot of heuristics into how our buildings are being controlled, and I'm sure the same happens here with the building. And yeah. Thanks.
I want to ask one question, because I have many, but I lost one. Everything you talked about is on what to do on the cyber side to have a better performance of the cyber physical side.
Yeah.
So I'm interested to see if you have any examples where what you learned from these two examples actually suggested an easy change in the physical side to give you benefits. Because that's a very interesting question.
Yeah, yeah.
There are examples that, but there are not many, and I think in cyber physical systems it's important to find that kind of application
So
and trust.
I can give you a small example that come out of this platooning. If you see a brand new truck today, they have something like I don't know if you call it fins or whatever. I mean on the side, they are really. And when you now think about going in this platoon, you can think about optimizing these type of, so to say, the air, the shape of the load or the carriage or whatever. You see what I mean. The box there. So in our, not what we have been doing ourselves, but in the collaboration, what they invest much more now in doing wind tunnel. I mean, they actually invested in new wind tunnel and thinking about redesigning some of these things according to a future scenario like the one we see.
The current curve, if I'm not mistaken, came from experiments in wind tunnel here by Jules Barlow many years ago, where they went from the square to the tracks. So the question is that still optimal if you have many tracks?
You mean the shape of the front of the truck? Yeah, that's another interesting thing, which I just learned through this project. You know, why is US trucks have this thing in the front, right? While the European are flat? No. That was not the answer I got from the truck industry. No, it's very simple. It's a legal thing. You measure the length of what is important when you talk about efficiency is the length of the truck, and you define the length of the truck differently in US and Europe. You see, so in Europe you could not put that in front because then that would include in the length. So then the part where you can put cargo would be shorter. So therefore they made it.
But they don't have separate the engine from the what you pull in Europe.
So the engine is basically under the driver.
Okay, here with
right?
the trucks that they have the driving platform is separated from let's call it the water.
Yeah. But
so the curve thing that they pushed here was the water caps that goes on the top of the driver cap, right? Where the driver at the beginning, if you remember, many years ago, it was like that. Then they put this curve thing. This was an extensive study here, and it was done explicitly to minimize drag on individual cars.
Oh, you mean just that separate that thing between? Okay, okay, I see.
And then Qualcomm came and they stuck in the communication for satellites, and they did this omni-track system. So you have multiple utilities in addition to the drag. The question is if you go to these multiple tracks. Is that still a good thing to have?
Yeah, this is exactly what I meant with this wind tunnel experiments and so on that is being invested in now. That they think about, how could you improve this, or is there a? Because we start talking about things which almost is like a train, right? And how should we now, But I don't have any deep comment on that.
The resume is pushing me to finish, so we'll finish. And welcome to come tomorrow. We'll have a lot more interesting discussions. Thank you again very much.
Okay, thank you.